Welcome to Lecture 8 for Chemistry 141. I've got a couple slides to pick up from the previous lecture, and then we'll get started in the new material. So we're taking a look at how all this concept of quantum mechanics works into an atom. How do we work that into the model of an atom? And we saw that electrons look at as a non-deterministic positioning. And what that means is that while they may have well-defined energies, they really don't have well-defined positions or trajectories. And so that means that a given energy, or an electron with a given energy, has several different possible positions within the atom. And so what we do instead is we define a probability map of where we are likely to find the electron based on its energy, and we call that probability map an orbital. And so that's a term that we'll use quite a bit during the rest of the course. Now, the equation that allows us to solve the equation of an atom and the electrons and where everything is called the Schrödinger Equation. And what that does is it relates the total energy of an electron and the actual energy of an electron and the wave function of an electron. So a lot of different complicated parts, and it has a very simple equation. H psi is equal to E psi, but the reality is the equation is actually quite complex. It looks simple, but is very complex. The capital H there is actually what's called a Hamiltonian operator, and so it's something similar to like a differential. And psi is our wave function, and E is the actual energy that we have for an electron. Now that wave function psi describes the wave behavior of the electron as it travels around the atom. And if we make a plot of psi squared, what that does is it gives us a probability density map of the electrons. And so that's what we call an orbital. So if we plot psi squared, we actually get where we are most likely to find the electron around an atom. Now, solutions to the equation can be found for a hydrogen atom or any other atom that only has one electron. So if you're looking at ions, sometimes that can be done as well. And so if we go back to what we were looking at about orbitals, really the way we're going to look at that is as a graphical representation of the wave function psi that solves the Schrödinger equation. Now each orbital has some different variables, and we call those quantum numbers. And these quantum numbers are related to each other. They're interrelated within the model there and within the equation. And those three quantum numbers that we're going to look at actually define the wave function. And so those quantum numbers are called n. That's the principal quantum number. We have L, which is the angular momentum quantum number. And we have the magnetic quantum number, m sub L. So these really define the wave function itself. And there is a fourth quantum number that relates more towards the electrons, and it's called the spin quantum number, and it's given the label m sub s. Well, let's take a look at each of these quantum numbers in detail here. N is really what determines the size and energy of an orbital. That's where the reason it's called the principal quantum number is it determines both the size and the energy of the orbital. It has certain possible values, allowable values, and these are just integers greater than 0, so 1, 2, 3, 4, etc. We can calculate the energy of, that should be an electron, in an orbital using the Rydberg Equation, and we have the energy for a level n is equal to negative 2.18 times 10 to the minus 18 joules times 1 over n squared. So the n here represents our principal quantum number, and our 2.18 times 10 to the minus 18 is called the Rydberg constant. And so this gives us the energy of any electron in an orbital with a principal quantum number of n. And if we calculate those energies, what we see is that as we calculate, or we go from one end to the next, the distance or the difference in energy between the end levels gets a little closer. So our greatest difference in energy is between 1 and 2. The next greatest is between 2 and 3. The next greatest is between 3 and 4, etc. So as you go farther away from the nucleus of the atom, so as n increases, the energies of the different energy levels get closer and closer. It doesn't necessarily mean that they get physically closer, just that the energies get closer. Our next quantum number is called angular momentum, and that is L. And L is what determines the shape of the orbital. And its numbers start at 0 and go up to n minus 1. So in other words, they can go from 0 to 1 to 2 to 3, all the way up to n minus 1. So as an example, if we have an n value of 1, then the only possible value for L is 0. If we have an n value of 2, then L can be either 0 or 1, and you will have orbitals with both an L of 0 and an L of 1. Now the value of L is often related through a letter designation of the orbital, and this goes back to some of the early spectroscopic designations of where electrons were. And so if we have a value of L, we call that an S orbital. If we have an L of 1, that's a p orbital. If we have an L of 2, that's a d orbital. If we have an L of 3, that's an f orbital. We don't do much with the f orbitals, but we do an awful lot with the s, p's, and d's. Next quantum number is the magnetic quantum number, m sub L, and this determines the orientation of a particular orbital in space. It has integer values that range from minus L to plus L, so those aren't ones in there that slide, those are L's. So let's say we have a p orbital where L is equal to 1. In that case, m sub L can be minus 1, 0, and plus 1. So we have 3 different values there. If L were equal to 2, then m sub L could be minus 2, minus 1, 0, plus 1, and plus 2. The last quantum number that we have, and we're not going to spend a whole lot of time on, we will in the next chapter, but this is the spin quantum number, m sub s. And this specifies the magnetic spin of an electron in an orbital. It only has 2 possible values, plus 1/2 and minus 1/2. And these are referred to as spin up and spin down respectively. So plus 1 is spin up, plus 1/2 is spin up, minus 1/2 is spin down. Now again, this number becomes more important and the concept becomes more important once we start occupying orbitals with electrons, and this is something that we'll do in the next chapter. So we're not going to spend any more time on that in chapter 3. Let's take a look at how we refer to our orbitals. We reference them mainly by looking at n and L values. And so if we look over here on our chart, we see that we've got the value says 1s, 2s, 2p, 3s, 3p, and 3d over here. So we've referenced them by the n equals 3, so that's our principal quantum number. And then we've referenced them by their L. So for n equals 3 and L equals 0, that's a 3s. For n equals 3 and L equals 1, that's a 3p. For n equals 3 and L equals 2, those are 3ds, etc. So that's how we reference those. The L value, again, is usually reported as that letter designation that we talked about earlier. And the number of sublevels that we see is equal to the value for n. So for sublevels, that's our L's. And so we see that for n equals 1, we have just the 1 sublevel. For n equals 2, we have 2 sublevels here. And for n equals 3, you can see we have 3 sublevels here. Okay, so the number of sublevels is always equal to n. The number of orbitals within a level is going to be equal to n squared. And so here we have n equals 1. So 1 squared is equal to 1. And you can see we just have that one sublevel. For n equals 2, 2 squared is equal to 4. And so we have, let me change colors here, we have 1 orbital there and 3 orbitals there, so we have 4 orbitals. For n equals 3, 3 squared is equal to 9, and so I've got 1, 3, which is 4, and then another 5, and so 9. So I've got 9 orbitals there in that level. And the number of orbitals in each sublevel is equal to 2 times L plus 1. So I'll let you do that math by yourself, since this got a little bit messy on there on that slide. But it does work out fairly easily. It's not something you really have to memorize, but it does give you kind of a handy tool to remember how many orbitals are in each sublevel. So now let's take a step back and go to spectroscopy. We talked about how the energy was emitted by an excited electron, and we looked at where it started and where it finished as far as its n level, and we looked at that excitation-relaxation process. So an excitation is the absorption of energy, relaxation is the letting go of that energy. So here we have excitation. Your book calls it radiation. I prefer the term relaxation. But we see where we have an atom or an electron in the n equals 1 absorbing energy from the n equals 1 and going all the way up to the n equals 3, and then letting it go back out from the n equals 3 to the n equals 2. It would then also release it from the n equals 2 to the n equals 1 in a later process. Okay, but it's this n equals 3 to n equals 2 that's going to give us some light that comes out that we can see in the visible range. So now that we have our energies of our energy levels, however, due to the Rydberg equation, we can calculate the energy lost or gained in going between either an excitation or a relaxation process. And we can calculate the frequency and wavelength of light that comes out from a radiation process. So let's take a look at the Rydberg equation. So we've got delta E, so the change in energy is equal to negative 2.18 times 10 to the minus 18 joules. That's times 1 over n final squared minus n initial squared. So this equation calculates the energy involved in a transition between two different n levels. Once we calculate that energy, we can calculate the wavelength. And here's an example that we will work out in class. Let's take a look at orbital shapes now. These are really what are dictated by the wave function, and these are the shapes that come out from the Schrödinger equation, and they're the results of solving that Schrödinger equation for a single electron. And our shapes become really important once we start looking at bonds that are forming between atoms, and the reason for that is because bonds are formed by the overlap of atomic orbitals, and so we need to look at where these orbitals are, where the electrons are, because that's, again, where we get our bonds. Once we form our bonds, those become very important in determining the shape of our molecules. So let's take a look at 3 of our different orbitals here. So we're going to look at S-orbitals. S-orbitals are generally spherical in shape, and for most orbitals, regardless of the type, we usually report those at a 90% probability. So we have a 90% probability of finding our electrons somewhere in that sphere. There's a 10% probability it's going to be somewhere outside that sphere as far as distance, but we can't really do a 100% probability. And we look at something that's called radial probability, and what we see is that we have a maximum probability of finding an electron at 52.9 picometers. So it's really very close to the nucleus of the atom there. And we see our equation here. It rises up from 0 right at the nucleus and comes up and then comes back down, and it decays here, and it never really ever reaches 0 because it is an exponential, and so it never reaches 0. So there's actually a probability, a finite probability of finding an electron pretty much anywhere in the universe for any atom. It just gets really small very quickly as you get away from that, away from the nucleus. So, but we see in that graph that we've got a maximum probability at 52.9 picometers, and as I mentioned, that probability tapers off, but is never equal to 0. And that's true for any of our orbitals there. If we go beyond something like the 1s and we look at the 2s and the 3s orbitals, they are still considered s orbitals, and so they are still spherical. However, inside the orbital, we get nodes of probability, and what a node is a region of 0 probability density. And the easiest way to look at that is the amplitude of a wave if you're waving a rope back and forth. And we can see that areas here, here, and here where it indicates nodes, there's 0 amplitude of the wave there. And if we look at the wave function of an electron traveling around an atom, and we consider that to be its probability density, then where the value of that wave is 0, then the probability density also becomes 0. And so there are areas where, because of the wave function, we have 0 probability of finding an electron there. And we can see how that works out with our graph of a 2s and a 3s orbital here. And we see that for a 2s orbital here, we've got a little bit of probability density here, and then a node, and then it comes back up, and so we actually have 2 areas where we're likely to find electrons, one much more so than the other. But then we have this dashed line right here, and this is an area where we have 0 probability of finding an electron. And then if we look at our 3s, we have a little peak there, a little bit larger peak there, and a much larger peak out here. So it's a larger orbital the farther out we go. But now we have 2 nodes, and so we have a node right about here. We have a node right about there as well. And so there's 2 areas where we have a 0 probability density of finding an electron. We can look at p orbitals, and p orbitals have an L of 1. So these start with an n equal to 2. So there's no such thing as a 1p orbital. We can only start with a 2p orbitals. And so we have 2p's, 3p's, 4p's, etc. These are symmetric within a plane. They are not spherical like the s orbitals are. And really what they look like is dumbbells, because they have 2 lobes of electron density. If you can imagine drawing a figure 8 along an axis and then spinning it, it's kind of what a p orbital would look like. And we'll take a look at some here in just a moment. They do have 1 node of 0 probability right at the origin, where our 3-dimensional axes meet. There are 3 p orbitals per level, and so that's because we have an L of 1, which means we can have an m sub L of -1, 0, and +1. And these indicate a different axis. So we have 3 different p orbitals that all lie along a different axis. So we have a px, a py, and a pz. But they are identical. They're just pointed in different directions. Let's take a look and see what they look like. So we've got our px orbital here. We've got our lobes lying along the x-axis. We've got our py. It has same lobes, but here it's just along the along the y-axis. We've got our pz here, which has its lobes along the z-axis. And we can see that we have a 0 probability for all these right in the center there. And this is where we have a probability of 0. This is a slightly different graph here. We don't really want to pay too much attention to that one. What it does indicate is as we go out along the axis, we go from a 0 probability up to some maximum and then down, and again we still have an exponential decay there that never really goes to 0. Well, that finishes out Lecture 8. It is some difficult material, takes a little bit to think about, so make sure that if you have any questions you contact us and make sure we get you straightened out. Good luck with this.